All right, let's go ahead and get going. Anybody have any questions about anything at all before we continue? Okay, so talking about power series, and primarily how to determine where they converge. So the last one we looked at was this series that really converges almost nowhere. Only converges when the series is identical to zero. So kind of looked at, and before that, what did we look at? Let me see. I think we looked at the geometric series, so the very base power series that converges when x is, the absolute value of x is strictly less than 1. So let's look at something a little more involved now. So I want to know for what values of x this thing converges. So our primary way to do that is going to be to see if these series end up, they're kind of, steady state long-term behavior, is to mimic a geometric series. So in doing that, we're going to set up the ratio test. So the limit as n goes to infinity of, the ratio of back-to-back terms. So what is a sub n plus 1 going to look like? 2x minus 5 to the n plus 1 over n plus 1. And one change I'm going to make this time is to basically write this thing out like this. Times n over 2x minus 5 to the n. Are we okay with what I've done so far? Okay. So I am trying to understand this limit. Can we go any further? What simplifies for us? Go ahead.
N plus 2x minus 5 to the power of n, and that leaves 2x minus 5 on the numerator.
Okay. So that happens. So the absolute value, let's try to separate this a little bit. So the absolute value of 2x minus 5 times n over n plus 1. Okay. So that was a big positive step. What can we do from there? This is a limit we can evaluate now. So I'm looking at this limit. I have two different symbols in here, right? N and x. As far as this limit is concerned, what is the variable I'm really looking at? N, right? So maybe we can do this. I'm going to just remove this thing. The expression involves x from the limit. So I'm specifically asking for what x values this series converges on. And I set up the ratio test. So if I specifically want to know where this thing converges, then what do I need this ratio test to deliver me? Like, is there something else I should be saying when I'm setting up the ratio test here?
It should be less than, the limit should be less than 1.
The limit should be less than 1 because that is the condition under which these things converge. So we have not been saying that, but that is absolutely an assumption we can make because that's all we're interested in. All we're interested in where we get convergence. So we might as well set up bring in the criterion for where series converge. All right. Now the only part of this limit, the only part of this expression that's still kind of up in the air is this. Can we evaluate that limit? What happens to this part of this expression as n gets very large? It goes to 1, right? So because of that, I have this, the absolute value of 2x minus 5 is less than 1. So we're getting closer, but I really want to know what values at x make this happen. So I have an absolute value inequality. If I say that a number has an absolute value which is less than 1, there's another way that we've kind of stated this before, right? This could mean that r is less than 1, but I think that's not enough. Is there another way to rewrite this? This absolute value of r is less than 1 without absolute values.
It's greater than -1, but less than 1.
Right, so it's, and I'm not sure if maybe you've never thought about absolute value this way, but when you're talking about real numbers, the absolute value of a real number tells you how far away it is from 0. So if I want my absolute value of r to be less than 1, then I just need it to be within 1 unit of 0. So we're going to extend that idea to what we have now. I need 2x minus 5, whatever that comes out to be, I need that to be less than 1 unit from 0. So I'm going to repackage this as -1 is less than 2x minus 5, which is less than 1. So kind of a new wrinkle here. Are any questions about the logic behind me doing that? Are we suspicious if that's even legal? All right, now can I start solving for x? If this is an equation, what would you do? I want to isolate x, so what's the good first move to do that? Add 5. So I can add 5 to all branches of this inequality, and I get -4 is less than 2x, which is less than 6.
Positive.
Yes. And then what? 2 is less than x, which is less than 4. I got no excuse. All right. 2 is less than x, which is less than 3. Okay, so we're getting really close. I know that everything strictly between 2 and 3, when every x value strictly between 2 and 3 will give me convergence. But one thing I should do is this. I should check the endpoints. So let's do that. Now let's think about this series. When x equals 2, what series do I get? The series from 0 to infinity of -1 to the n over n. Does this series converge? So one thing I want to point out, that now that we're fixing x, we're choosing a single value for x, it's no longer a power series, right? This is like the series we've been looking at for the last week or two. Does that series associated with -1 to the n over n converge? It should, right? Now, what if I have x equals 3? And this series becomes the series from 0 to infinity of just 1 to the n, right? 1 over n. Does that thing converge or diverge? That one diverges. So ratio test showed us that every x value between 2 and 3 gives us convergence. But what else do I have to include?
The 2.
2. So I think this is my full set of x values that gives me convergence. That half closed interval. So and x is between 2 and 3, including 2, excluding 3. So we did quite a few things to get to the end there. Any questions about how we built that up? Okay. Keep on going. How about this thing here? So same game, same story. I want to find out the values of X on which this thing converges. So what's a good place to start? Or do we need a hint? So how we started the last few?
Ratio.
Yeah, so let's set up the ratio test again. Hopefully some of these nasty things cancel out. So as n gets very large, I want to look at consecutive terms. So this becomes -1 to the n plus 1 times x to the what? 2n plus 2 over 2 to the 2n plus 2 times n fact, no, not n plus 1 factorial squared times the reciprocal of all this stuff. 2 to the 2n times n factorial squared all over -1 to the n x to the 2n. Okay, so this is hectic. Does anything simplify for us? Go ahead.
So we cancel out -1 in power and we just a little bit into 1 in numerator.
Okay.
And then we cancel out the x to the 1 power and then we just leave it with x squared in the numerator.
Good. So anything with anything where the index shows up in an exponent will help us. So we're going to have a -1 left over in the numerator. We're going to have a 2 squared, I think, in the denominator. And then we're going to have an x to the second. In the denominator. And what about the factorials?
And then we have n plus 1 squared because we cancel out the factorial of and operation, and estimation.
Yeah. Does that account for everything? I believe it does. Okay, so got rid of a lot of stuff. Anything else?
You get rid of the -1.
The -1 is going to get handled by the absolute value. Does that mean the absolute value goes away?
Yeah.
So typically we have to worry about x, right? Because x can be negative.
Oh, yeah.
But in this case, x is being squared, right? So I believe the absolute value is not doing much. So I have x squared over 4 times n plus 1 squared. And again, I want to know where this converges, so I'm going to force convergence basically. I want to know where this thing is less than 1. Is this a limit we can look at now? Maybe it would be helpful if we pulled the x squared out because that's not factoring into the limit. So the limit I'm really looking at is 1 over 4 times n plus 1 squared. Is this limit now something we can talk about? What's going to happen to that is n gets really, really large. It's going to go to 0. You have a constant numerator and a denominator that's increasing. Like an x squared times 0 is less than 1. So what does that mean about x? So now I essentially get 0 is less than 1. So what does that mean about the values of x for which this thing converges? To all of them, right? So as long as x is a real number, is this a symbol we've seen before? That I'm drawing badly? So basically, the very last step we have there shows that the ratio test converging has nothing to do with x, which means x can be absolutely anything. This ratio test will always, this ratio will always deliver a value less than 1. So this very strange looking series here converges absolutely for all values x. How we doing? Okay, so we've seen the 3 possibilities basically of the way power series can converge. So we dealt with one that was centered somewhere, some distance from 0. But if you have a power series that looks like this, so some list of coefficients times x minus a to the power of n, so the powers are growing. We saw one series that converged only at that single value of x. So really not a good representation. The other extremes of what we just saw, where it converges for every single real value of x. And the middle ground here where there's some finite, finitely long range of values for x where we have convergence. So one thing I want to point out here is that when we have this r, should I give it a name? Yeah, the radius of convergence. We know we converge inside that radius and we diverge outside it. What this theorem can't guarantee for you is what happens on the boundaries. So those are the things you're going to have to look at, kind of on a case-by-case basis. So those are, when we're talking about the convergence of power series, those are the 3 possibilities you have. You either have a single value where it converges, you have all values that it converges on, or you have this window that has a strict minimum and a strict maximum where we have convergence. Questions about this idea here? So just kind of building up where we started. When we first started talking about sequences and series, the only language we had was convergence and divergence. Then to that convergence, we added absolute and conditional convergence. Now we're talking about, okay, well, it converges somewhere, figure out exactly where. So just building more specificity onto the idea of convergence. Specifically convergence, if it diverges, we're kind of done looking at it. It's not all that interesting. Questions? All right, so now let's find the interval of convergence, which has something to do with the radius of convergence, but got to find the radius first. So I'm trying to find out, same kind of question, where does this power series converge? So what's the best tool to help me answer that question? Ratio test. So we'll set that up. The limit as n goes to infinity of this ratio. So absolute value of -3 to the n plus 1 times x to the n plus 1 over the square root of n plus 2 times the reciprocal of the original. All right, then I want this to be less than 1. Anything jump out at you that we can simplify? Does the -3 do anything? So in terms of the -3 to the power of n terms, They cancel completely? Does anything remain?
-3.
I have a -3 in the numerator, which remains. How about the x to the n's?
The x to the n's cancel, the units x.
So I have x in the numerator, and then I don't believe the square roots will cancel. So I'll carry them. All right, what else? One thing I'm gonna try to encourage us to get in the habit of is the x has nothing to do with this limit really. So I'm gonna pull that out. Knowing that it might be negative, so I'm gonna keep the absolute value bar on it. So what happens with the rest of this, we'll have 3 times radical n plus 1 over radical n plus 2. And I want that to be less than 1. Is this a limit we can evaluate? What's going to happen to the numerator and denominator as n starts to increase? So the numerator and denominator are both going to increase, they're both going to go to infinity, and they're both going to grow at the exactly the same rate. So we could, kind of treat it like being, if the verbal description convinces you, cool. Otherwise, we could set up L'Hopital's rule to make that more clear. But I will tell you that limit is 3. So I have the absolute value of x times 3 is less than 1. Which means the absolute value of x is less than 1/3. So this right here, I'll underline it, we're not quite done, but this right here is my radius of convergence. I know that as long as x is less than 1/3 of a unit from 0, if I'm inside that radius, I'll have convergence. But now, so let's start building up. The x values that I know I'll get convergence on are these. And 1/3 of the boundaries. Anything like on the interior of this, so anything strictly bigger than -1/3 and strictly less than 1/3, I'm going to get convergence for it. Anything outside of that, strictly outside of that, I'm going to get divergence. So the last thing we have to look at is what happens on the boundaries. So how many points do I have to test? 2. So just do them one at a time. And these are not going to be, they're not really going to be power series anymore because I'm not allowing x to vary. I'm fixing x. So I'm looking at this series when n is equal to -1/3. So I get -3 to the n times -1/3 to the n over radical n plus 1. Is there any simplification that happens in there?
Yes.
How so? So in the numerator, both of these terms are raised to the same power, right?
Yeah.
So I can do this, I can collect them. -3. -3 times -1/3 to the power of n. What is -3 times -1/3? 1. Simply 1. So this series becomes 1 over radical n plus 1. Don't think I can simplify it anymore, but do I know what that series does? What should it do? So one thing we've talked about before is this idea of a p-series test or a p-series theorem. If you have a series that looks like this, where it's simply 1 over n to the power of p. Where does, for what values of p does this thing converge? So it converges when p is greater than 1. It diverges when p is less than or equal to 1. What's our p value down here? 1/2. So that means what? This diverges. So we have to leave off negative 1/3 from our interval, but what about positive 1/3? So this becomes the series from of -3 to the n times 1/3 to the n over radical n plus 1. So kind of in the same way that I simplified the numerator last time, -3 times 1/3 is -1. So I have -1 to the n over radical n plus 1. What does this series do? We said the non-alternating one diverges. How about this one?
Well, wouldn't it converge because it's like it's always alternating between like negative and positive, so it's like not adding up any value.
Right? Do we have a test that does that we talked about? Do we have tests for alternating series? I can't give you a bigger hint than that. So this converges. So by the alternating series test. So let's remind ourselves, what is that? How does that test work? So this alternates, right? What does the non-alternating part look like? It looks like the series above it. So that 1 over radical n plus 1. What has to be true about the non-alternating part of the series to use that test?
The next term has to be less than or equal to like the previous term.
Right, so it has to decrease as you go from term to term. Will that decrease as n gets bigger? What's happening to your denominator? It's getting bigger. Your numerator is a constant. So that works. I believe the non-alternating part has to be positive, strictly positive. I think that's good. And the limit of the sequence has to go to 0. So all those things are met, so I get convergence for that value of x. So how does that change my interval here? I'm going to include the right end boundary. Oh, no. Gonna get mad if I try to circle it, so we'll just leave it like that. Questions? Go ahead.
Can you consider the interval of convergence?
Yeah, so the radius is basically the radius is the interior. Or another way to say this, the radius tells you how far the boundaries are from each other from your center point. But the radius alone does not tell you what the interval is, because the interval answers the question of what's happening in the boundaries. So I call this the radius of convergence. I call this more specific thing the interval of convergence. So the radius will not tell you what happens at x equals 1/3 and x equals -1/3. You have to do a little bit more digging, some kind of case testing to figure that out. Questions? Can we do one more? All right, how do we start? Where's your tests? Right, so that n plus 1 times x plus 2 to the n plus 1 over 3 to the n plus 2. times 3 to the n plus 1 over n times x plus 2 to the n. One that's be less than 1. All right. Hopefully a lot of stuff simplifies, does it? Give me an example.
Can simplify, like, 3n plus 1 times 3, and then cancel out 3n plus 1. And then you can also do,
So what remains when you deal with the threes?
the remains is, like, it becomes 3 over, I mean, like, it becomes, you want like the whole simplified thing? Or,
I mean, so there should be a 3 remaining where though?
on the bottom,
Right, good. Okay, so 3 remains in the denominator.
and then also you can simplify the x plus 2n times, then like, it becomes x plus 2.
Where?
Like on the top.
Okay.
So, x plus 2 times n plus 1.
And there's still an n here, right?
Yeah.
Okay. All right. That's good. So I'm gonna pull out the x plus 2. I'm just gonna deal with the things that have a n in them. Why don't I pull out the third as well? So the limit I have is n plus 1 over n. What is that limit? It should be identical to 1. So I have this thing here. Absolute value of x plus 2 over 3 is less than 1. Which implies what?
Absolute of x plus 2 is less than 3.
Means now I can write this as a branching. Like we have 3 different branches here, so -3 is less than x plus 2, which is less than 3. So I get -5 is less than x, which is less than 1. All right, good so far. Are we done? No. So find our radius of convergence. And I think I misspoke last time. Radius of convergence is not an interval. Our radius convergence is really, in this case here, the radius of convergence is equal to 1/3. Basically, how far from your center point are you going to get convergence? So that is strictly 1/3 here. The interval tells you kind of a lot more specifics about what x values they are. So what's our radius of convergence here? 3. But now we have to do some work and figure out exactly what that interval is. So we've done a lot of that. But now what's the last thing we have to look at?
You have to test the limit.
We have to test what's happening at the boundary. So when x is equal to -5, we get the series from n to 0, n equals 0 to infinity of n times -3 to the n over 3 to the n plus 1. Can we tell what that series does? Can we do any simplifying? Okay. So n times -3 to the n over 3n times 3. Does that help? So remember, we looked at a past example where I think I'm sure you're all much more comfortable with the idea that if they have the same base and different exponents, you can deal with those things. But you can also deal with them if so I have unlike bases, right? -3 and 3, but they're both being raised to the same exponent, right? Which means I can, take those together. So -3/3 to the power of n. The series. Times n/3. So what does this become? It becomes -1 to the n times n/3. Does that converge? No, how come?
Because the numerator is growing.
So the numerator is growing and the denominator is constant. So it's just, not only is the series not going to converge, the sequence underneath it all doesn't converge. So we got divergence at x = 5. What about when x = 1? What does that series look like? N times 3 to the n over 3 to the n plus 1. Any ideas yet?
Then you have n/3 because then you can into this one.
Okay, so now I have this series. What does that one do? Pretty much for the same reason. It doesn't alternate, but it's still going to grow without bounds. So here's our full interval of convergence. We got divergence at both ends. We know that on the inside of this set, we have convergence. So our interval of convergence is right here. How are we feeling? Okay, so that is all I have for you from this section. So let's go ahead and do some more things with power series. So one of the things that I mentioned at the very top of this chapter was one of our major goals was to build up some techniques for turning any function you can think of, any continuous function there is, and treating it like it's a polynomial. So that's kind of what power series allow us to do. So I think we've talked about this series, but maybe not in this exact way. Maybe we went the opposite way. I want to represent this as a power series. Is this a series we've talked about? What is happening as I go from one term to the next here? What's that? Multiply by x. So what kind of series is this then? It's geometric, right? I have a common ratio. So then we should be able to set this up as a power series, both kind of in sigma notation and using and as its sum. So this is a geometric series, right? How do I find, this implies it's going to go on indefinitely. How do I find the sum of a geometric series?
1/1 minus the common ratio,
Is it always 1 over?
or the first term.
Right. So yeah, it's always the first term over 1 minus the common ratio, which in this case is 1/1 minus x. So this is the sum. But something else we should think about is this. I want to figure out how to set up this sigma notation. Any ideas there? Another way to think of this is I want to know basically, can I define the sequence? So basically, instead of adding all these terms together, treat them as a list. Can I generalize this sequence for any value of n?
You like the first term times the common ratio raised to the nth power.
First term times the common ratio raised to the nth power.
Yeah.
Does that always work for a geometric series?
Yeah, I think so.
It should, right? So it does work here. I think we can generalize that, and that's, so let's circle this because that's what I wanted, but I think for any geometric series, we can say this, the geometric series. So from n equals 0 to infinity. So instead of 1, we can generalize by saying what?
A sub 1.
A sub 1, the first term. And instead of saying x, we can say what? R, whatever, we usually would call the common ratio is R. To the power of n, right? So I've seen a lot in both your notes and your homework and stuff. I've seen a lot of people like write down kind of like a template for what a geometric series looks like, the way you define it. It doesn't quite look like that. Does that cause a problem for anybody? I think what at least a few of you are used to is this. So, I mean, we started off this chapter talking of kind of the default we were using for a very long time was that sequences and series, their first index is 1. And now we've kind of shifted to our first index being 0. Are we okay with the fact that the two sigma notations I've written down there are essentially the same? Okay, so yeah, I mean, if you're kind of relying on some past ideas that still work, you just got to be a little more careful about how they're defined. So what we're going to try and do here is we're trying to take functions. So instead of taking a series and building it up into a function, now we're going to try to go the opposite way. So I have this function here, f of x equals 1 over 1 plus x squared. And I want to represent this as a power series. So I think for this first one, the question I'd like to ask is there any, do you see any similarities that we can rely on between 1 over 1 plus x squared and 1 over 1 minus x? So maybe I'll just write that down here. We said that 1 over 1 minus x was equal to what power series? 1 plus x squared plus x cubed, and so on. So how did we get that relationship? What is that based on? Why does 1 over 1 minus x equal that sum?
The common ratio is x, and that's like the formula.
Okay, so the common ratio, so basically the thing on the left here is a formula for the sum of a geometric series. The thing on the right we said is a geometric series. Can I use that up there in the margin to give us on the inside about this thing? 1 over 1 plus x squared. Could I look at this as the sum of a geometric series?
The first term is 1.
So the first term is 1. I like that.
The common ratio is negative x squared.
The common ratio is negative x squared. How'd you get negative x squared?
Well, if it's 1 minus r, and then it's plus x squared, you have to put the sign.
Okay. Good. So can we write out a few terms here? What will be the next term after 1 here? What's that?
1/2.
1/2. So we're trying to generalize this for any x. So we said the common ratio was. So we said the first term is 1. Common ratio is what?
Negative x squared.
Negative x squared. So then what would the next term be?
Negative x squared.
Negative x squared, then?
Negative x to the 4th.
Oh, you lost me. Almost had it.
Oh,
And then? okay with that? All right, so we've seen the first few terms. I'm gonna buy more parking. I'll ask you another question. Can we generalize this in a series notation? We said this was a geometric series, right? And we said we had something that was more or less generalizable for sums of geometric series, or not sums, but expressions of geometric series. So can I use that to build up this sigma notation here? How would I do that? What did we say last time? We said first term times the common ratio to the power of n. So our first term is 1. What's our common ratio? Negative x squared to the power of n. So are we okay with this series, negative x squared to the power of n? Make sense? Now, can I find the interval of convergence of this thing? How do I find the interval of convergence? That's confirmation duration test. So now basically, this is kind of the one of the major additions here. Instead of me giving you a power series and asking where it converges, I am telling you to build a power series, then tell me where that converges. So working from the functions and treating those as series. So what is the limit as n goes to infinity of this ratio? So that's going to look like negative x squared to the n plus 1 over negative x squared absolute value. I want that to be less than 1.
We're gonna be to the end, the bottom.
Yeah, absolutely. Thank you. Good catch. All right, where do I go from there? When you cancel out, what are you left with? Negative x squared. So what does that tell me? Isn't the absolute value of x squared less than 1? Do I even need the absolute values? I don't think they're doing anything. If I square something, I don't know if you've ever seen, so one of the definitions of absolute value that is totally true is this: the square root of x squared. So squaring something inherently makes it positive. So I don't need the absolute value. It's not really doing anything extra.
Isn't there is there parentheses around the negative x?
Yes.
Okay. That makes
Yeah. Does it make sense that there are? Or do you think there should not?
Yeah, no, it does. I just thought there wasn't any on the far right. And
Yeah, because there's nothing else to kind of segregate it from. That's the only reason I left them off. All right. X squared is less than 1. What does that tell me about x? Is x less than 1 enough? What if x is negative 10? Yeah, I still have to bound it below by negative 1. So that's our interval of convergence, or at least part of it. What should we still really look at? The bounds. What kind of series do we say this was? It's geometric, right? Is it okay? So do we need to look at the bounds in a geometric series? Does a geometric series converge if the common ratio is 1? Let's look at one. Is this a geometric series? 1 plus 1 plus 1 plus 1 plus 1 plus 1, and so on. It is. Does that converge? No. What about this? 1 minus 1 plus 1 minus 1 plus 1, and so on. Does that converge?
Yeah.
No. It's not gonna like blow up to infinity or anything, but it is. Like, what's the sum of the first million terms? 0. But if I had another term, it's -1. If I had another term, it's 0. So it doesn't blow up to infinity, but it doesn't settle either. So because of that, I don't have convergence on either side. So that's one thing that we probably didn't, I probably should emphasize more, but for a geometric series, I do not have convergence of the boundaries, only strictly between or strictly on the inside of that set. All right, I kept you long. Any questions last minute? All right, I'll stick around for a bit if you want to talk. Otherwise, I'll see you tomorrow or Wednesday.